So I'd like to take off from where we left off in the last class, when we had just introduced how you can split up the magnitude and the phase contributions of a linear time invariant system when it is excited by a sinusoidal input. So to quickly recap what we discussed in the previous class, what we had was a linear time invariant system to which we saw that if you apply an input of the form e to the power st, the output turns out to be g of s times e to the power st, where g of s is the transfer function of the LTI system. And by extending this, we saw that if you instead choose, so let me just write this as u of t is equal to, and this is y of t is equal to this, right? So let me now just again recapitulate what we had shown in the previous class. Instead, if you now choose u of t to be something like a cos of omega t, then we saw that we can split that up as a upon 2 e to the power j omega t plus e to the power minus j of omega t. And because this is a linear time invariant system, in fact, per se, because this is a linear system, we can see what the response due to u2 given by a cos omega t would be if we know what the responses respectively due to a by 2 e to the power j omega t and a by 2 e to the power minus j omega t are. Okay, and now we use this result, so we know that eventually y of t turns out to be a m of omega cos of omega t plus phi of omega, like so. So this is what our output is going to be under these circumstances. We've already seen this in the previous class, where of course m of omega is equal to the magnitude of g of j omega, and phi of omega is equal to the phase of g of j omega. Right? So in other words, if you look at it as a dual problem, that is, suppose you're given this linear time invariant system which is unknown and you're asked to identify this. Think of it as an experiment. You have a bunch of inputs that you can apply to this, and each of those inputs is of this particular form with a variable omega. So this is for the experimental purpose. Yeah. So you apply sinusoidal inputs or cosinusoidal inputs of different frequencies, and you see what the output is for each of those inputs, and from there you can measure what m of omega is and what phi of omega is. And this will allow you to plot these two functions, m of omega and phi of omega, versus omega, where omega is the independent variable. So now think of it this way. You want to determine the actual transfer function, that is g of s, or you can also say g of j omega, all right, based on the plots that you have generated for m omega and phi omega experimentally. So what do you need to know? You need to know that what sort of a combination of m omega and phi omega would lead to what kind of a transfer function. So this is a reverse mapping. In other words, first there's one question, which is given a particular transfer function g of j omega or g of s, what would the m omega and phi omega look like? That is the direct question. We shall see that shortly in this lecture. But the reverse question is, given m of omega and phi of omega, is g of j omega or g of s uniquely determinable? Can you determine this uniquely? If so, then this plot of m omega and phi omega will also allow you to identify the linear time invariant system with which you are experimenting. So this can be posed as a question of system identification. All right. So before we move further, a couple of points that I would like to emphasize on. First, notice that y of t is given by a times m of omega cos of omega t plus phi of omega. All right. Notice first, m of omega and phi of omega are independent of a. Okay. And second, the frequency omega of the input is the same as that of the output. So this is only true because the system we are dealing with is linear time invariant. So if this weren't a linear time invariant system, this idea of performing an experiment that allows you to apply sinusoidal inputs of different frequencies and plotting m omega and phi omega correspondingly to identify the original system will not work. So I want you to bear that in mind. So throughout the course, right from the beginning, we have emphasized on the definitions of linearity and time invariance. And now you can see the pieces coming together. Why we were actually so keen on understanding, because these properties do have significance, even in a problem such as system identification here. All right. So I just wanted to get that out of the way. Another small clarification. This is exclusively for some students in my division who asked me. So while discussing this question of having an input e to the power st being applied, resulting in an output of g of, excuse me. Yeah. Having this output given by g of s e to the power st. So here, look, you can just multiply this e to the power st with g of s. Yeah. But in general, if you are applying a cos omega t instead, you don't really perform a multiplication. Yeah. You don't just write this. This will be incorrect if you just write this as g of some j omega cos omega t. That is incorrect. That is just not done. So the notion of this m and phi, so when you write it in this term, it just turns out to be m of s, just a minute. So if you now replace, so I'll just take the easy route out here because I can. So suppose you just write this as e to the power j omega t here, j omega e to the power j omega t. Yeah, so you can write this as mod of g of j omega into a unit vector with angle g of j omega times e to the power j omega t. You can write it like this, but in case of the sinusoid, you cannot do that analogous thing. Yeah, the only way you can relate with this is if you write this as a sum of two such exponentials, one being e to the power j omega t, the other being e to the power minus j omega t. So in some sense you cannot have an exact correspondence here, but nevertheless, because we know that m of omega is equal to m of minus omega and phi of omega is equal to minus of phi of minus omega. That is to say that this is an even function and this is an odd function. Therefore, if you know this magnitude, which is m of omega, and this phase, which is phi of omega, just as it conveys information about the response to this exponential input, so also does this convey information about the response to this cosinusoidal input. Yeah, because you know that m omega and m of minus omega are the same, and to obtain phi of minus omega from phi of omega, you just need to multiply it by a minus 1. Yeah, so that is why, provided you know what m omega and phi omega are for the exponential, you also know how to sort of deduce what the input or what the output for the cosinusoidal input will be. Yeah, so don't make the mistake of thinking that this is also a similar multiplication like we do in case of the exponential. That's not the case. Yeah, in fact we've already explicitly mentioned that expression. So that is the expression. It appears in this particular form rather than as a product. Yeah. Okay. Quickly wanted to get that out of the way. So now we want to write explicitly what the expression for m and phi are. So we know that m of omega is equal to magnitude of g of j omega, which is given by square root of the real part of g of j omega whole square plus the imaginary part of g of j omega whole square, and phi of omega is equal to tan inverse the imaginary part of g of j omega divided by the real part of g of j omega. Right? So all this we've already done. I'm just recapitulating all this because there's been a significant hiatus between the last lecture and today. All right? Anyway, we actually took steps further away from this. So we also showed that how in Bell Labs the standard was to consider, instead of just gj omega, 20 times the log of gj omega. And we explained why this 20 was significant, right? First of all, the multiplication by 10 was so that the graph was displayed in a nice fashion. Yeah, so that the spacing was sufficient. So that's what took the unit from bell to decibel, which is written as dB. All right, multiplication by 10. Multiplication by a further factor of 2 was due to the fact that, okay, by the way, this should be with base 10. So multiplication by a further factor of 2 resulted from the fact that the net gain or the amplification was in terms of power, but the measured variables were voltages. So since power is proportional to voltage square, and when you take the log, so log of power is proportional to twice log of voltage. Yeah, so that is what resulted in this factor of 2. So anyway, coming back to this problem, now you see, again, please recall that these are just repetitions. So at the cost of boring you again, I'll still do this. So what does this say? This says that this is g of j omega e to the power j phi of omega. Yeah, let me just erase the later part of this so that I can make space here. All right. Fantastic. So then I'll just do the intermediate steps. This is m of omega, yeah, and this is e to the power j phi of omega, which turns out to be 20 log m of omega plus 20 j phi of omega times. So I think in the last class, if I recall correctly, I had missed this factor. Please incorporate this correction. This is a constant factor, by the way. You can call it some gamma. You can just replace this as some gamma. The important point here is that by splitting it up in the log form, you see the real part is exclusively a function of m omega, and the imaginary part is exclusively a function of the phase. Yeah. So that is the interesting bit. We further went on to explain in the previous class that because you want to accommodate a wider range of frequencies, what we do is we choose the log scale on the independent axis. So this is what we do. We have this omega. So remember, it never starts from a 0 because log of 0 is undefined. So you can choose some very small value here. Let's say 0.001. And let's say you have 0.01 here. So these are equispaced on the log scale, all right? Because this is log with respect to the base 10. Then this is 0.1. Then this is 1.0. Then this is 10.0. And this is 100. Sorry, that's 100, not 1,000. Okay. So this is 100. All right. So these are equispaced. Even if I have not made a very good job of it, please assume at least that these are equispaced. All right. So this is our independent axis. And now what we do is we try to draw plots. So remember that these are the same axis, omega. It's exactly the same here. It will be 100, it will be 10, here you'll have 1, here you'll have 0.1, here you'll have 0.01, and it will start from 0.001. So on the same graph, we want to draw this phi of omega. Of course, you can consider the gamma, but even if you let go of the gamma, it's just a scaling factor. Remember in the previous slide, we just showed that this gamma, this log of e to the base 10 is a constant. Yeah, so you can just, it's probably somewhere close to 0.3, a little over 0.3. You can ignore that safely. Yeah, so 20 times 0.3, that's around some 6 times. You can just safely ignore that. And this just comes out to be purely the phase function. Right there. And this, if you consider to be 20 log of m omega. Okay. Then what happens is this becomes a linear scale. So for instance, here you can have 0 dB, you can have, let's say, minus 20 dB, here you can have 20 dB, here you can have 40 dB, sorry, dB. Actually, you can write big B or the small b, it doesn't really matter. In the Bell Labs, initially they used to write small b, but now in many of the textbooks you'll find the convention is to write a big B. So either way, be consistent about whatever you use. Okay, so this is how it would look, right? So this is the magnitude function and this is the phase function. So this, of course, you can plot in degrees. So let's say this is some 0 degrees, this is, let's say, minus 45 degrees, somewhere here is, let's say, minus 90 degrees, and so on and so forth. So on this graph, you can use a semi-log graph paper for this purpose. A semi-log graph paper would have a linear scale on the y-axis and a logarithmic scale on the x-axis. All right. So the semi-log graph paper, now we want to see how to plot the magnitude function, the log of the magnitude function and the phase function. So this is what the Bode plot is all about. So how do we go about this business? All right, we'll come back to this pretty often. This is basically the main content of this particular lecture today. So let us try to find out a method that will enable us to sketch these Bode plots, at least approximately. Just like we did an approximate sketch of the root locus, if you remember. We'll not really go for exact sketches. There's always really no limit to the amount of perfection that you can master. So we'll not go for that. We'll be happy with reasonable approximations of these plots. So let us typically look at what a typical transfer function of an LTI system would look like. Okay, so we start itself with g of j omega because we are not really concerned about s here. We are looking at the steady state response. So therefore we start itself with g of j omega. Now remember, this is very important. When you dealt with root locus, so for a root locus, the way you wrote the transfer function was something like s minus zi, I is equal to 1 to m upon I is equal to 1 to n s minus pi times k. This was the standard form for the root locus, yeah, the root locus problem. This was the way to write. So every method that you use has a particular standard form. So now that we are dealing with Bode plots, the moment you're given a transfer function, you have to cast it in a particular form. And what is that form? That's what we shall now see. So given any transfer function, you always split it up in this form. First you have the k, and then you have something like this. I is equal to 1 to m1 1 plus j omega tau zi times product of I is equal to 1 to m2 excuse me j omega over omega n zi square plus 2j zeta omega over omega n zi plus 1. Okay, so that takes care of m real zeros and 2m2 complex zeros. All right, divided by, again by the same token, zeta. Okay, sorry, I missed the subscript for zeta. Zi, so zeta pi omega over omega n pi plus 1. And there's something else missing here. You could also have poles or zeros at the origin. So we will also further consider terms such as j omega to the power r. So this is the standard form. I want you to remember, every time you are given a problem, you have to write it in this form. Unlike in the root locus case where you wrote it as products of s minus zi and s minus pi terms, here you have to pull out all those terms in this way, and this is the standard form for doing the Bode plot. All right, so this is how you have to do it. So where r is an integer positive or negative, we'll rule out 0. I mean, if 0 is there, then it really doesn't make sense in writing this. And it's a type 0 system anyway. Yeah. K tau zi tau pi zeta zi zeta pi omega n zi omega n pi, all of these are real numbers. Yeah, so this is the standard form. Okay, so what we are trying to do now is, when we think about this particular plot here, 20 log of m omega, we're basically saying that we want to plot, again, if I miss out on this 10, please remember when I write log, it's with base 10. If I wanted to write the natural logarithm, it will be with, I'll write something like ln. All right, but that's not relevant here. Every time I write log, it's always with respect to base 10. So that's something like this, log all right. So now you see the point here. So, products of numbers, this is equivalent to sums of their logs. This is basically the fundamental starting point of logarithms. And what have we here? We have this transfer function written in the form of products. Yeah. So this allows us to decompose piece by piece this transfer function g into building blocks. What sort of building blocks? Building blocks such as terms like these, or terms like these, or terms like these, or terms like these. So if in theory we know what the magnitude functions or functions such as these corresponding to these building blocks look like, then we can technically add them or subtract them, as the case may be, because products are sums, quotients are differences. All right. The main idea is that products and quotients reduce to sums and differences when we take the log. So now that we've written it in this form, in the product form and quotient form, all right. So therefore, if we look at each individual block, and if we are able to figure out what the magnitude plot or log of this magnitude plot of each individual block looks like, then we are done, because then we have the building blocks. What we then need to do is just add them, and we are done. So carrying that thought forward, what sort of building blocks are we now looking at? Terms like k, terms like terms like j omega to the power r is an integer, terms like 1 plus j omega tau to the power plus minus 1. So it's a plus 1 if it's a 0, it's a minus 1 if it's a pole. All right. And terms like j omega over omega n whole square plus 2j zeta omega over omega n plus 1. Again, to the power plus minus 1, depending on whether it's appearing as zeros or poles of the transfer function under consideration. All right. So the point is that if we are able to determine what do the functions, m omega phi omega look like for these elementary building blocks? Our hope is that if we can find out what they look like for these elementary building blocks, then we can just sum them. And it's easy to sum two functions on a graph. At least graphically, it's very easy. At every point, you just take the sum of the magnitudes or the values of the two functions, and you get the net resultant function. So if you plot for each individual block, for example, each individual block here, if you are able to plot m omega and phi omega for each individual block there, then you'll be able to construct or cook up the entire m omega or phi omega for the overall transfer function, that is this. All right. So far we've just spoken about this m omega. Yeah. So that might set you to ask the question, right? So what about the phase? So let's just briefly discuss what the phase looks like. Look, the phase is already, you know, if you take two complex numbers, z1 and z2, and you multiply them, and you write z1 is equal to r1 with an angle phi 1, and z2 is equal to r2 with an angle phi 2, then the product is basically r1 r2 with a phase phi 1 plus phi 2. So the beautiful thing here is, see, not only when you take this logarithm, of this function here, not only does it split up beautifully into the real part which corresponds to the magnitude function and this imaginary part which corresponds to the phase function, but also when you're plotting here for each of those individual blocks, you need to carry out the same operation. That is to say, if you have plotted, let's say, the magnitude plots for certain individual building blocks, you just need to add them to get the composite magnitude function for the overall transfer function. Similarly, if you plot the phase for each of those building blocks, again, you need to perform the same addition, because as I said, in products of complex numbers, the phase only gets added or subtracted. So it's essentially in this plot, overall plot, it's going to be the same thing, same operation that you do. Take each individual block, plot its magnitude plot and its phase plot, plot them individually, separately, and then sum them together. This will be clearer, so don't fret over it if you don't understand this clearly at this juncture itself. We'll revisit this with an example. Maybe not, if not today, then in the next lecture. But we'll surely do an example that will clarify this point. I want you to appreciate that this is a beautiful method, nevertheless. All right. Okay. So now, as I was saying, we have been able to sort of split up into the building blocks. We have been able to at least see what the building blocks of an typical linear time invariant system's transfer function are like, and those are exactly objects like these. Okay. All right. So let's just start with what these look like. So I'll take the next few slides to just plot the magnitude and the phase. Let me just take this. Remember, this is not 0 because this is a log scale. I just like to remind you of that, because intuitively, because it is very usual for us to assume that we are dealing with a linear scale, intuitively you might always feel that this is a 0, but it's not 0. You cannot plot a 0 on a log scale. I know I have said this, but I want to repeat this and put it on the record. All right. So here we want to draw 20 log m omega. Scale is in decibels, so I'm using big B, and this is phi of omega, let's say in degrees. So the first candidate that we are looking at is the term k. So 20 log k. How does it vary with frequency? It does not. So it's a constant. All right. So whatever this value of 20 log k is, let's say it's some alpha. Okay, so then on this graph, let's say you take the point alpha, it's a constant flat line. That's what the magnitude plot is for the term k. What about the phase? What's the phase of a constant real number with zero imaginary part? What is it going to be? It's going to be 0. So let's say this is my 0-degree line. So the phase plot is going to be just another constant 0. So we've at least tackled the first block. We know how this is going to look. All right, this is done. So now we focus our attention on the second block. Okay. Again, as before, the block under consideration now is, let me just say that R we will consider for 1 and -1. For other integers, we will see that it's very analogous. So what is, if j omega is equal to j omega whole to the power r, then m of omega is equal to mod of gj omega is equal to just omega to the power r. This is magnitude. So therefore 20 log of m omega is equal to 20 r log of omega. All right, what about the phase? What's the phase of this number? See, it's j, so it's basically g of j omega is equal to j to the power r omega to the power r. So therefore the phase of gj omega is equal to it's 90 degrees, right? For every j there's a rotation of 90 degrees, so it's a phase contribution of 90 degrees depending on the sign of r, whether it's plus or minus. This will be either a negative phase contribution or a positive phase contribution, and you know that for especially for 1 and -1 it's either an integrator or a differentiator. We've just discussed this when we were discussing controller design using root loci. All right, so then what should the plot look like? Okay, let's just take this to be, I'll draw the same scale here, 0.01, 0.001 is my starting point. I'll not repeat it here, okay? I'll just draw the points, I'll just not write the values again. 0.1, 1.0, 10.0, 100.0. Okay, cool. So there we are. Now we want to draw phi of omega and 20 log m omega in decibels when our function under consideration is j omega to the power r. As I said, we shall consider the typical cases of r is equal to 1 and -1. But before that, what is the first rule for drawing a plot? We need to at least know some points where we know its value, the value of the function. So what is that point, the easiest one to evaluate? You see, if you take this, okay. So if you take this to be the 0 decibel marker, then what do we know? At a value of, oh my goodness. You see what I just did there? When you choose omega to be equal to 1 and pass on the argument inside the logarithm, yeah? When you pass on the argument 1 inside a logarithm, it always leads to 0. So it will always pass through the 0 dB line at omega is equal to 1. What happens at omega is equal to 10? Yeah, that is a curious bit, and that is exactly what's going to lead us to our answer. And this is a very simple, straightforward answer. Now see, if you have minus 20, minus 40, so these are in decibels. So this is 20 and this is 40. So what is the value attained at 10? So log of 10 is unity, yeah, 20 times that. So if r is equal to 1, then we know, I'm sorry, I should use different colors probably. Excuse me. Oops. Okay. Right. So this is for r is equal to 1. All right. You see what I just did there? Okay. So when you take log of 100, it's 2. So 2 into 20, it's 40. All right. And on the other hand, let me change the color. Let me change it to green. If you had taken r to be equal to minus 1, then this is what the point would have been. Is it not? And yeah. So basically, I will now draw the plots for. Please note that this is a straight line on the log graph, even if it doesn't look very straight from the awful drawing that I'm doing here. Excuse me for that. So just a minute. So this is for r is equal to minus 1. And for the other one, this is for r is equal to plus 1. So what do we know? Over a range that's called a decade. Remember, this is 1 decade, just as this is 1 decade. So over 1 decade, the frequency increases by 10 times. That's called a decade on a log scale. So over 1 decade, there is a change of 20 dB. Is it not? So over 1 decade, now erase this. This is just for indicating what a decade is. So over 1 decade, there is a change of 20 decibels. Yeah. Now if r had some other integral value other than plus minus 1, then the change is 20 r dB per decade. So in general, the standard method for drawing the magnitude Bode plot for a component such as this, for a block such as this, is as follows. Locate the 0 dB line at 1, at a frequency equal to 1. Okay, at omega is equal to 1, that's where your 0 dB must pass. And thereafter, the slope would be given by 20 r dB per decade, and it's a straight line. So that is what the magnitude plot would be like. All right. Now coming to the phase plot. So what would the phase plot be like? As we've already indicated, I'll just draw this so that you can see here. Let's call this 90 degrees. Let's call this 0 degrees, and let's call this minus 90 degrees. So again, following the same convention as before, we have the phase plot for r is equal to +1 and the phase plot for r is equal to -1. All right, great. So now we know, at least for two of the blocks, the constant block and the block of the kind j omega to the power r, how to draw the Bode plots, the Bode magnitude and phase plots respectively. So we'll stop here in this particular segment chunk of the lecture, but the lecture continues into the next segment. This is just for recording purposes that I've split it up into smaller blocks. We'll continue with this in the next segment, which is coming up immediately. Thank you.